Hey everyone, we are here today to talk about friction problems. So let's dig in. To start, it's important for us to know what friction is. And friction is a resistive force generated by the interactions between two surfaces. Now, if we think about what this means, it's important for us to recognize that so far we have been using a relatively straightforward model when we talk about motion. We've been using something that we would call the point particle model. Basically, that just means that all of the objects, the balls, the boxes, etc., that we've been talking about, we really just kind of pretend they exist at one location and all the forces act at that location, and that there's nothing about the two or three dimensionality of the object that is particularly important. And honestly, like many models, which we discussed when we talked about gravity, that's a very valuable way of thinking about things. And it's pretty much true most of the time that things do behave that way. However, there are a few things that we really do need to consider um, the actual object itself in order to really grasp motion, even at this very straightforward level. And so we're going to think about, when a box is on a surface, what we are thinking about here are those two surfaces that are interacting. And specifically, we're thinking right here, if we zoom in on those two surfaces, what's going on? And even if they're very, very smooth surfaces, at a molecular or even atomic level, there's going to be some amount of roughness to them. Now, maybe they're very rough, or maybe they're just like a little rough. But at that level, something is going on with those surfaces. They're not perfectly smooth. And this is where we start to get some friction happening. So, what happens when we have friction is that essentially those two surfaces sort of interlock. Okay. And so when we go to push that object, we can't just automatically start the object. We kind of have to free the surfaces before we can actually start to push it. So when we're trying to understand friction, it's important for us to understand there's kind of two things that can make friction smaller or larger. The first thing is, and we kind of talked about this here, the surfaces themselves. So how much the surfaces interact. And generally speaking, that is a measure of how rough the surfaces are. Now we use a new variable when we're talking about this. It is a Greek lowercase mu, if you're looking for how to spell that, mu. And it's basically a cursive U that has an extra long left leg. And this is the coefficient of friction. It is unitless, which, by the way, anytime in physics that you see the word coefficient, you should know that it means that it's going to be unitless. We'll look a little bit later about why this doesn't have a unit, but it's a measure of how rough the surfaces are, how much they're interacting. And it does apply to a pair of surfaces. So you can't just say like ice has a coefficient of friction of 0.1 or carpet has a coefficient of friction of 0.2. It matters what's on the ice, what's on the carpet. Is it cardboard carpet? Is it a metal ice? Like that all matters. Mu for any pair of surfaces is going to be typically between 0 and 1. So it's essentially we'll find out kind of a percentage, right? So 0.5, 0.7, 0.3, these are all very common numbers we'll see for coefficient of friction. Now, if they're any greater than 1, that doesn't actually work if it's just friction. In that case, you would probably be dealing with something that has like a glue of some sort going on. So first thing that tells us how much friction we're going to have is the coefficient of friction, which is a unitless number, mu. The second thing that tells us how large our force of friction is how hard the two surfaces are being pushed together. And this is actually a number we already know. It's our normal force. So as you recall, when we talked about normal force before, and I'll link that video here as well, normal force or support force is how much the table or floor or carpet, whatever it is pushing up on the object to support it, to keep it from falling through. And so that is how hard the surfaces are being pushed together. And we write that as Fn, although I've told you that there are lots of other ways to write that as well. And luckily for us, the force of friction is pretty straightforward. It's just these two numbers multiplied together. Now let's think back. I said that the coefficient of friction is unitless. So if we think back, really what this is saying is it's what percentage of the normal force turns into a force of friction. That's how I like to think of it, at least. And that's it. So this is the very basics of friction. I am going to tease one additional element of friction, and then I'll do a whole separate video about this because when I teach friction at like the introductory level, this is something we only do kind of conceptually, and then I dig into it a little bit more when we talk about friction at a more deep, more mathematical level. So like in a, for instance, AP class. But it is important for you to understand, at least conceptually, the difference between static and kinetic friction. So static friction is when an object is stopped and we want to start it. And I actually love that, static, stopped, and start all have kind of those first two letters the same because it makes it really easy to remember. Kinetic, which we'll also talk about this word when we get to energy, is when the object is already moving. So if you've ever had like a really heavy box of cardboard books on a carpeted floor, you may have noticed that it's really, really hard to start the box moving. But once you get it moving, if you can keep it moving, it isn't as hard anymore. And that is actually the difference between static and kinetic friction. And to explain this, it all goes back to those interactions between those two surfaces. If they're really tightly interlocked like this, right? To start an object moving, we have to separate them. And that takes a lot of energy. It takes a lot of force. But once we get them separated, as long as we can keep them moving along relative to each other, they don't have the time to form back that tight interaction. And so that is why when we're looking at friction, the force of static friction is always greater than or equal to the force of kinetic friction. It's harder to start things moving than it is to keep them moving. Now, I put an equal to there. If two objects are very, very smooth atomically, then like it's pretty much the same. There's not a lot of this like interaction that we have to undo. So it is important to realize that there are some materials, very, very smooth surfaces for which that equal to will happen. All right. I think this is a good place for us to stop if we're looking at just the basics of friction. Thanks so much. Have a great day.